Thank you everybody for being here in the afternoon, the last afternoon. So it's a pleasure to see that the room is quite full. And we are reaching the last session of the summer school, and this time we are going to have two representatives from the Declarative Programming Group in this school. And the first one is going to be Rafael Caballero, that's going to talk about the declarative debugging. So Rafa, thank you very much for being here and for making it possible.
Thank you. So, yes, my talk is about declarative debugging, and I will try to do an overview of all the branches or all the possibilities of declarative debugging. And please interrupt me with any question or observation. I know there are some people related to declarative debugging. So maybe they can make this presentation more live and more interesting. I also will ask you questions to do the talk more interactive. And, well, this is the summary of the talk. First, an introduction, and I will explain the basic ideas of declarative debugging in this part, and also in this part about computation trees. And then I will concentrate on three different cases: functional logic programming, relational databases with SQL, and finally Datalog and declarative debugging. These are three cases of applications of declarative debugging, because declarative debugging is a general technique that can be applied in principle to any programming paradigm. So first, the introduction. I will start with explaining about bugs and bugging systems. We have here some software, maybe hardware component system, and it has several components which are related to each other somehow, and then we expect that this system produces some beautiful output like here, but we know that unfortunately sometimes, well, this is the intended semantics because it's what we expect. I will talk about a lot about intended semantics. It's what the user has in mind, how the program must work and how the components must work. But unfortunately, we have bugs. So we have a bug in some component, the system, we don't know where. Well, we don't know that there is a bug, except why? Because we see that there is an unexpected result. This is not what we expected at the beginning. So when we see this, we know that we have an unexpected result. We call this unexpected result an initial symptom. The symptom that there is something wrong. So we know already that our system is buggy, but we have no idea of what's going on. So we only know that there is something wrong here, but not what. Where is the bug? Is the problem? I don't know if anyone sees the bug. The bug is here, but it's difficult to find the bug in a complex system. That's where declarative debugging comes to help us. Declarative debugging is also called algorithmic debugging. Some people insist in calling algorithmic debugging, others insist in calling declarative debugging, and there are some fights about the terminology. But I would use algorithmic or declarative instead. The characteristics this is a general paradigm-independent framework for debugging. It concentrates on semantics. So what we will do is to compare the intended semantics and the actual computation results. It's the idea of declarative debugging. We will detect erroneous components, so we will not examine the components. A component can be a method, a function, anything we wish. That the only characteristic that all components must have is to have an intended meaning, something that the user can have in mind about the behavior. We have this is a black box approach because we are not looking at the code. In declarative debugging, we don't need to see the actual codification. We only need to know the semantics, as I said before. So in declarative debugging, we have that each component has an intended semantic, of their behavior, and we have an oracle. This oracle is someone or something that knows these intended semantics. In particular, they must know, or she must know, whether actual computation is wrong, non-valid, or valid with respect to the intended semantics. So the oracle with a concrete computation must know if this is wrong, this is wrong, this is valid, this is valid. Okay, if we know that this is wrong, this means that the result that this component is wrong. And now a question, this means that this component is wrong? Has some failure in the implementation? Because we know that the result is returning is wrong. Who says no? Why?
Because the problem can come from another component.
Yes, this is important. This can be wrong because it takes input from here, which is wrong. So when we have some method in Java that is returning some unexpected result, it doesn't mean, we know that it doesn't mean that the method is wrong. Maybe it's using another method which is producing a wrong result. So this is the idea of declarative debugging. Well, this is I'm talking about the oracle, which is quite enigmatic, usually in the papers about declarative debugging. And well, the oracle can be in practice either a computer system, for instance, a trusted specification. We will talk about this later. But unfortunately, usually, the oracle is simply the poor user. So we like to say the oracle because it seems that there is someone outside that knows everything, but in practice, the user must know how the components behave. This is the bad part of declarative debugging, because the questions sometimes can be complex, difficult. Maybe there are a lot of questions. We will talk about all of these issues in the talk. Okay? So, well, as I said, detecting that a component C is producing an invalid result implies that there is a bug in some part of the program, but maybe not in this component, because there is this sentence, garbage in, garbage out, is true, so maybe the method is receiving some erroneous input, and therefore it's producing an erroneous output. And our goal is to detect components that are really wrong. Well, the idea to do that is we have two ideas. The first one is we are looking for components that contain or produce a non-valid result in a particular computation, and that all the components connected to C, or more in particular, producing inputs that are taken by C, contain valid results. So we are looking for components receiving valid inputs and producing non-valid outputs. This is really an erroneous component. Well, this is the first idea. We are looking for this kind of components. And the second idea used in declarative or algorithmic debugging is to employ some data structure, usually a tree, to represent the connection between components in the erroneous computation. So we will use computation trees, and computation trees will say, okay, this component depended on this and this another component in this particular computation. To finish this first part, this small overview, I would say that declarative debugging has been applied to a lot of languages. To declarative, first it was introduced in declarative languages. The first reference to algorithmic debugging was produced by Shapiro, who in 1984 introduced algorithmic debugging in the field of logic programming. The reason is that in declarative languages, declarative debugging is very convenient, not only because it's called declarative, but because declarative languages are very difficult to trace. So in Java or C++, these languages, we have the traditional trace debuggers that go step by step. And we can examine the variables, the results, and everything. But training something similar in a declarative language is more complicated. Why? Because there is a part which is called the control, the machine that is under the language, that is translating some high-level sentence to some low-level behavior, and sometimes it's very difficult to exactly say what is the result of a function call, for instance, in Haskell. Well, you say, okay, I can take the input and get the output. Well, this is not so easy, for instance, in Haskell, because it's a lazy language. So maybe you have a call with some function, and the function is not evaluated at that moment, and maybe it's evaluated later, and maybe it's evaluated partially. So to perform a trace is not so easy. Logic programming is easier, but it still is pain in the neck. Everybody that works with Prof knows. So Sapiro introduced this in the field of logic programming, and soon other people like Nilsson, Sparuth, and Linash applied this to functional programming. Actually, Linash was the first one suggesting that this framework could be applied to many different paradigms. Was the first one to think about object-oriented programming, for instance. There are all other applications, like in mod. Here is Narciso and Adrian, who have worked in declarative debugging in mod. We have also functional logic programming, deductive databases, and a lot of applications. Object-oriented programming, there are some people also, David Saiz here and Josep Silva have worked in Java, and also in SQL. I will talk about SQL later. Now we are working in this case. So now we go to computation trees. Talk about computation trees. The computation trees represent the computation that produce an unexpected result, what we called before the initial symptom. So we are trying our program, we get some unexpected result, and the debugger will build a computation tree representing this erroneous computation. Each node in this tree will contain some intermediate result R, which corresponds in the case of the root to the initial symptom, and a reference to some component. So each node has some components associated, maybe in Java a method, maybe in Haskell a function associated to this node. And, well, there is some relation between parent and children. The children of a node N must contain the intermediate results needed to obtain the result at N. The results that were used by the parent. Yes?
You said you were doing black box testing.
Yes.
So you don't have access to the code, but you have a reference to a fragment of code, so I don't understand.
Yeah, you don't have access to the inside the fragments of code. You determine which fragments you are using, for instance, methods. And the user who is debugging doesn't need to have a look to inside the method. But the debugger will have a look inside, because the debugger checks that this method calls to this one and this one and this one. In that sense, it's not black box. You're right.
It's black box from the point of view of the user.
Only from the point of view of the user, who doesn't need to know how each component is implemented, only their semantics. In that sense, I said black box. Maybe it's only from the point of view of the user. In fact, in declarative debugging, the person that is debugging doesn't need to be the same person that implemented the program, because they only need the documentation explaining the semantics of the components. They don't need the code. But the debugger needs the code in order to produce a fix. Okay. So, well, we will start with logic programming because it's the easiest case, and it's quite easy to understand. Here we have a logic program with Tweety and Sylvester. Here we say that Tweety is good. We also say that Sylvester is good, and this is an error. This is a bug in the program. Maybe we cut and paste and we didn't check everything properly. We also say that Tweety is loyal and that someone is trustable if he or she is good or loyal. We also say that Tweety likes Sylvester, which is true. And we also say that Sylvester likes Tweety, which is true, but in a different sense. It's true. And finally, we say that X is a good friend for Y if X likes Y and X is trustable. Okay? With this program, here a component can be a predicate or a clause, depending on the level we work. We can try this goal. Please tell me all the pairs X and E and Y such that X is a good friend for Y. And we get these three answers. The first one is because Tweety is good, the second one because Tweety is loyal, but the third one says that Sylvester is a good friend of Tweety. And we didn't expect this in our intended semantics. This is not true. So we have an initial symptom, and we want to debug this. But we don't know where is the error. Of course we know because it's in red here, but usually you can imagine that it's difficult to know. So the user, the poor user, needs a declarative debugger or some kind of debugger. In this case, a declarative debugger. So we build the computation tree. The computation tree, observe that this is the root. The root is not the same as the original goal, which was with X and Y, but it's the original goal instantiated by the wrong answer. Because we are concentrating on the computation that produces this answer, only this answer. We have that Sylvester is a good friend of Tweety, and this is because if we go to the program, Sylvester is a good friend of Tweety because Sylvester likes Tweety and is trustable Sylvester. So here we have the same, likes Sylvester Tweety and is trustable Sylvester, and Sylvester is trustable because he's good according to our program. This computation represents, this tree represents the actual computation. Now, what we need to do in declarative debugging is to check this actual computation with respect to the intended model. We already know that this is wrong because the user has detected this as the initial symptom. Therefore, we ask questions to the poor user who's here thinking, and we ask, is it true that Sylvester likes Tweety? In a strange way, but yes, so this is valid. We represent this in green. Is it true that Sylvester is trustable? He is not. And is it true that Sylvester is good? And he is not. So now we have all the three with colors. Green means valid, red means non-valid. And now we can know that good is the cause of the error. Because trustable is in red, but has an erroneous input, which is good. Also, good friend is in red, but has an erroneous input. But good is in red and has no erroneous input. We can say in general that all its inputs are valid. In this case, there are no inputs, so all of them are valid. So we know that the bug is good. And the debugger can say, okay, then good is the wrong part of the program. Observe that in declarative debugging, the declarative debugger doesn't say the error is in this sentence in particular. So if you have in Java, maybe it will point out to a method, but it will not say inside this method is in this particular sentence. Of course, you could take a group of sentences and think about this intended semantics, but you don't. We usually think about methods. We'll say this method is wrong, but not which part of the method is wrong. This is a drawback, or maybe we try to teach our students that they must write small methods with very few sentences. So if you know that a method is wrong, you know a lot. It's easy to replace the method by another one. Yes.
Right, but it can tell you which input output.
Yes. Yeah, this is very useful. So we say not only that good is bad, But in this case, that good Sylvester is bad. You talk about this. And this is important because I'm not saying, okay, replace the whole predicate good. But in particular, there's an instance, which is this one, which is wrong. And this is useful because here we have, in this case, only two, but maybe many clauses for good. And it's pointing out to this one, to this clause in particular. In general, it will point out to an instance of a clause, and this is useful concept. Okay, so we have this, and now the user is a little bit happier because he knows where is the error. He doesn't know how to repair, maybe, but he knows where is the error. So the goal of declarative debugging is to find what we call buggy nodes. What's a buggy node? A buggy node is a non-valid node with only valid children. Or thinking in terms of red and green, a red node with green children. Only green children. Or with no children. Because a leaf, a non-valid leaf, is always valid. It's a particular case. Well, it's easy to prove, and at least it's very easy to think now and also to prove. That if we assume a non-valid root, we always assume a non-valid root because we are starting all the time with an initial symptom, which is the root of it. So we always have a first red node. Well, if you have a green and red tree with a red root, then it's easy to check that there is at least a buggy node connected to the root, by a path of non-valid nodes. The idea is that you can start here. I think it's easy. I don't know. Can you see the whiteboard? Not really. A little bit better here. Well, if you start with a red one, then you go to the children. If all of them are green, you have found already the buggy node. If any of them is red, you repeat. And in this way, finally you will find a red node with green or in this case black nodes. So we have a buggy node for sure, and well, this property is the completeness of declarative debugging. So in declarative debugging, independently of the particular language, we have completeness in the sense that we are starting with a initial symptom, and therefore we have a buggy node for sure. This is a little bit not so straightforward because there is an assumption here. I'm saying that every computation tree with non-valid roots contains at least one buggy node. This is true, but there is something else. This is true if the user, the oracle, answers correctly all the questions. Because otherwise, maybe you won't get the buggy node, or will get a node pointed out as buggy, and maybe it's not buggy because the user made some error answering the questions. So this is true modulo of the user. Okay. And how computation trees can be obtained in general? There are two ways explained in the papers about this technique. The first one is to define a program transformation. A program transformation such that the new program, we have a program and produce a new program, the debugger produces a new program, such that behaves as the initial one, except because it also produces the computation tree. We can think a little bit about this now, but it can be done. So the components return their own computation trees after the transformation. The pros of this approach is that it's very convenient for proving correctness. We can define the program transformation formally and to prove that the transformed program really produces computation trees in the sense we have defined it. But it's very slow. Usually it's very slow. You must take a program, transform the program, and this usually takes some time. And also the program takes more time to execute because you are producing computation trees that usually are huge structures. So we are here all the time with small examples, but real computation trees can have thousands of nodes, and therefore write a function that returns this huge structure is usually quite impossible. So the second alternative was to modify the runtime procedure, the runtime system. Somehow, the compiler or the compiling of the system has two modes. The first is the normal one. The second is the debugging mode. And when you are working in the debugging part, it executes the program and at the same time traces the program producing the computation. So there are these two different approaches. This is more dirty, but you need to modify the system, but it's much faster. There are some, I think, in Haskell there is
You're assuming that the structure that you get, is a tree. So it's restricted only to cases when stuff happens.
Sorry?
What I mean is you can have cycles.
You can have cycles in a program, you mean?
Yes. You have.
But you're talking about non-terminating program or recursive programs?
No, mutually recursive.
Mutually recursive, but terminating.
Yes.
Yeah, then it's no problem. In the computation trees, you can have Fibonacci of 3 that calls to Fibonacci 2, which will be a child, which calls to Fibonacci of 1, and then it stops there. And this is not a problem in the computation. So programs can be mutually recursive, but terminating computations are not.
For every single input, it's.
Yeah.
No, but you compute the tree for
each input.
For an input.
For an input, for a particular input. That's the reason. We are not working in some abstract diagnosis framework, but in a particular computation. Anyway, you pointed out to a problem of declarative debugging, non-terminating problems.
Usually, a problem, you are trying to find the reason for a problem. And the way you found the problem is because the computation finished.
Yeah.
So you had a finished terminating computation that you are just representing as a tree.
What if it's non-termination?
Then declarative debugging cannot be applied. This is one of the problems. So maybe you can consider, okay, if the clock reaches the 4 o'clock and still waiting, then I have a wrong answer and an initial symptom. But still, declarative debugging is not valid in this case. This is the main limitation of declarative debugging. So, we have these two. For instance, here with this program we talked before, we could think. I haven't written the transformer program, but we could think. Yes.
Unless I guess that you can detect that you're repeating the same state, which is the same as you saw previously, right?
Yeah, in principle, but you're not sure that it.
You're not sure, but
yeah.
if you detect that you're in the same state and you're looking again, you're going to repeat the history, you can stop there and say that at this point there is something wrong in my program.
Yes.
Or with a finite trace.
Yeah, there are some people working in that direction, so you can break the program when it's looping, or say, okay, the debugger just wait 10 seconds, and then take the trees you have, try to detect the cycles if there is any one, or try to debug the incomplete tree. The problem is that you usually in the nodes you have a call and a result, and if it's not terminating, probably you have no result at the top, and then it's more difficult to debug. But some people are doing that in Java, for instance. Well, here is the same program, and I haven't written the transformation, but we could think of a program transformation. I could take another argument here and say, okay, good, returns Tweety, and a structure that says computation tree, good Tweety with empty children, because this doesn't call to anyone. I don't know if you follow the same. So I'm trying to perform a program transformation on the fly. So I could take this program, produce a new one with a second argument here, a last argument, which is the computation tree. In this first case, could be a structure CT computation tree with a good Tweety as first argument, and the second, the list of children. In this case, the list of children will be empty. In this case, also empty. Here also. But here we have trustable x. We'll have another argument, computation tree, trustable x with a children. The children will be the tree returned by group x. See? In this case, we have 2 children. In this way, it's easy to see that we could produce a transformed program that returns the transformed. In logic programming, what Shapiro and Lloyd and other people proposed was instead to write a meta-interpreter that execute the program and produce it. So the second approach. Okay, so we can talk about a general declarative debugging schema. We can distinguish these 4 phases. The first one, we have an initial symptom, which is detected by the user. The user must say this was wrong, unexpected. The second one, the debugger builds the computation tree for this erroneous computation. By the way, this is another drawback or something that must be taken into account. I said that the debugger is building the computation tree after the initial symptom is obtained. This means that the debugger must repeat the computation. Maybe the program is taking several inputs, asking questions to the user. Then the question must be asked again, which can be, I want to debug this program, then I will execute it. The debugger says, I will execute the program, and I will ask you everything, and you must repeat everything. This can be not the best option. So in some declarative debuggers, what they do is when you are working, trying some program, you are storing all the inputs someplace, so you can repeat the computation, some kind of trace by default. Then the tree is navigated. We didn't talk about navigation yet. We will later. Navigation is you are looking for a bugging node. In the small example, we have seen the debugger asked about all the nodes, but maybe we can do it better. In fact, we can do it much better. And finally, a bugging node is detected, and its associated component is pointed out as a row. So from the theoretical point of view, the completeness we have seen is ensured if the user asks correctly all the questions, but the soundness must be established. So we must prove that a bugging node implies an incorrect component. It depends on the definition of the tree. We must define a suitable tree such that a bugging node means there is something really wrong in there. It's also interesting to prove that the debugger generates suitable computation trees. This is related to the transformation programs I said before. It's a good way to prove that the computation trees. About the soundness, the idea can be to use some semantic proof calculus such that parent nodes correspond to conclusions of inferences in this calculus and children to the premises of the same inference. So the idea is I want to prove that this computation tree is really good. It works for this paradigm, for this language. Then you get some calculus, semantic, some calculus that give the semantics of the language and try to produce the computation trees associated to this calculus. So for instance, in the case of, this is the idea, you have this inference, you have here the conclusion, and here's the premises, and this corresponds to this as computation tree. That's the reason Adrian likes to write the trees in a different way, with the root at the bottom, like this. So for instance, logic programming is a good example because there is only one rule, which is the variant of the modus ponens, which is usually used. And we say that if we have something like this, this should be C, sorry. This is the head and this is the body. Then we can prove this instance if we prove the instances of the premise. This is true. This is a very simple calculus, but it's enough, and this is what we used in the example before. It's how the tree of Twiggy and Sylvester was built. So a bugging node in this case means this is red, this are green, this is not valid. This means that we have this instance with all of these are valid, this is not valid. This means that this formula is not valid in the intended model, and therefore the clause is not valid in the intended model because it has an instance which is not valid. So we are proving this very, very simple way that these proof trees are valid for debugging logic programs. Only in this instance. When the languages get more complicated, the calculus will be more complicated. Things also become a little bit more difficult. We will see this in talking about functional logic languages. Well, we must also talk about different types of errors, declarative debugging. The example of Tweety we have seen was an example of wrong answer. We got something that we didn't expect. But there are other errors. We can also talk about missing answers. A missing answer is I get all the answers and I miss one. There is one that was not produced by the program. This is also an error. We call this a missing answer. Well, in the case of a wrong answer, the cause is an incorrect clause, as Lloyd proved in 1987. And in the case of missing answers, the case is an uncovered atom with an incomplete predicate. So it's a predicate in the program that is not complete. There is some clause that is not able to produce some atom I am expecting. Missing answers are more difficult to debug. We can think why now. Well, first I will introduce a missing answer example. Here we have again Tweety, which is good. Also grandma is good. Trustable in this case is only good. Tweety likes grandma, Tweety likes Sylvester, but we forgot to introduce grandma likes Tweety. This is the same before. X good friend for Y. If X likes Y and X trustable. And we can try this low. And we have only two answers. The first one, Tweety likes grandma. The second one, Tweety likes Sylvester. But we expected this third answer. Grandma likes Tweety. And the answer is not there. So in this case it's different because with a wrong answer we said this particular computation producing this particular result was wrong. Here we say this set of answer does not include this answer I was expecting. You can see easily that it's different. Also, declarative debugging can be applied to this case. I'm not talking much about missing answers because here are more difficult, but we can try to think a little bit. And it's easy to check that the proof calculus I was using is no longer valid because this proof calculus is valid for a particular answer. I can prove using this that Tweety likes grandma. But I cannot prove that something is incomplete because you must collect all the answers to say that something is incomplete. I don't know if you see the difference. So you need a new, we call this kind of calculus positive, and we need a negative calculus that says, okay, from this goal here, you have a set of answers which is X is Tweety and Y is grandma, or X is Tweety and Y is Sylvester. This kind of facts, more this bigger notes. Then we can say this note is not valid because it's incomplete, not wrong but incomplete. This makes things more difficult. This makes the same computation tree no, because now we have more complicated nodes with more information. The same program transformation, no. In fact, it's quite difficult to obtain a program transformation for missing answers in Prolog, which is logic programming, because logic programs obtain each answer separately. And now you need a program transformation that produces all the answers together. So of course you can use and collect or something like that, but you must be very careful with the bindings of the variables and everything. It's not so straightforward. And also the inference rules is not the same. You need a new calculus that includes the completion of the program. negative case. So it will not talk much about missing answers. Okay, now it's time to confess the limitations of the declarative debugging before we go to the particular cases of functional. So the first one is what you said. Non-terminating bugging computations don't have a computation tree because you are waiting, it doesn't stop. You cannot say that you have an initial symptom there. And then declarative debugging is not directly applicable. So you have this system, this is the user who's waiting for the answer, and the time goes and goes. There is no answer. There is no initial symptom or anything that you can use. Yes.
But the lack of termination is the initial symptom.
No, you know it's not because well, if you can talk about minutes. Say okay.
Yeah, you cannot spend an hour waiting for the program, then
maybe it's a slow one. You don't have patience. You must be more patient.
Yeah, but you have in the same way you have an oracle saying that this is right or wrong, the oracle may also determine whether this shouldn't take longer than...
Yeah, the oracle can say after 7 minutes in this particular computer, this is an initial symptom, but this is not very related to semantics. So you must create a new semantics that says this goal must obtain this answer before 7 minutes.
But you cannot abort the...
Yeah, you can abort, but then there is no result, and then there is no computation tree.
But there is a wrong input.
A wrong output? No, there is no output. Input.
If some of the components, so if it doesn't terminate, maybe it's because...
Maybe it's not, maybe it's just very long. That's the reason. You cannot be sure. Unless you have a semantics with time or... So you say, okay, Fibonacci of 1000 didn't end in 6 minutes. What's the meaning? Maybe your computer is slow or...
well, I mean from the practical point of view.
Yeah, from the practical point of view I agree, but we are working with semantics. So you need a semantics that takes this practical point of view into account. This is not easy, or not, I mean, at least not straightforward. More comments on this? Okay, this is one of the limitations. The other limitation is related with concurrent programming. So if you have several threads that maybe interact, it's very difficult to obtain a single tree. You have like several threads. Each one could be a computation tree, and it's very difficult to have the view of a whole component, and you have a forest, in fact. Sorry?
We complete in the same.
Yes, and yes, you're completely right. And this is very typical of concurrent. When you have a wrong computation, it's very difficult to repeat, and we need to repeat the computation to train the tree. So the only possibility is that you are tracing at the same time you are computing when you are testing the program, but you are changing the program, and maybe you will get a different result when you go to the real case. So this is the reason. So even in case like Java, when you have events with buttons, and you press the button, and then a different thread starts, or a different part of the code starts, it's difficult to create a tree. It's possible, but it's more difficult. It's not so straightforward. I think David is have worked that option. Josep and you have worked on the case of Java, and maybe. Yeah. Not threads, no, but events. Buttons, and it's possible, but it's more. You must concentrate on a part of the computation to get that. Well, this is another limitation, and now we go to the drawbacks. So sometimes it's difficult to determine the validity of the intermediate results. You need the debugger will ask you, this is valid. Sometimes you say, okay, I don't know. I knew that the initial symptom was wrong, but I don't know all the details about the intermediate. This is true. And there are many possibilities, but at the end we always get complex questions. It's true that if you use, for instance, in Java, the trace debugger, you also have the same questions. when you are using the trace debugger in Java, step by step, you say, okay, this method, I will jump over this method and check the result. If the result is wrong, I will repeat and go into the method. Everybody does that. They are doing declarative debugging somehow, and they are checking the validity. So you need to know if a component is working or not. But this is true that sometimes we can get complex questions, and there are several workarounds to solve this problem. So here, for me, it's difficult to know which one is the right one, always. This is valid and this is non-valid, but the question can be complex. So another drawback is that the system can ask too many questions to the user. This is more easy to solve in practice. You can have huge trees, but there are some ways of navigating the tree to ask as few questions as possible using some techniques of navigation. So you have many questions, and the poor user doesn't know how to solve this. But the answer is to use good navigation strategies. Also, Vicente Silva and David have been working on that. There are a lot of navigation strategies that take into account the size of the tree and the form of the tree and try to ask as many questions as possible. And for instance, the more typical, I will explain the naive part of the divide and query. Divide and query, the idea is, well, the first idea is to go, when you are looking for a buggy node in a tree, is to go up to bottom, top down. You know that the root is non-valid, then you ask about the validity of all the children. If all are valid, you are done. The root is valid. And if you find a non-valid children, you repeat. Well, this is the first strategy, but it's not a very good one. There are many better than that. And this is another one. The idea is to look for a node which is called the center of the tree. The center of the tree in the sense that the subtree inside this down this node is approximately equal to the tree that is out of this tree. Usually it's not possible to find a center, but the node that is more close to the center. And then you ask about this node. There are several ways of choosing this node, but then you ask about this. If this is valid, you can remove the whole subtree. Why? Because we have said here that there were a buggy node connected by non-valid nodes to the root. So if this is valid, there is a buggy node here, some part here. And in declarative debugging, we are only looking for one buggy node. Maybe we are losing some buggy nodes inside, but we don't care because we are looking for just one buggy node. There is an error. Maybe there are 100 errors, but we will start with one. So we can remove the whole tree, and if the tree is non-valid, this node is non-valid, then we consider this as a new computation tree, because we have already a non-valid root, and we can repeat the process. With this technique, you divide more or less, depending on the size of the structure of the tree by 2 each step. Of course, if you have a very wide tree, it doesn't work very well. But usually this is why it works very well. And the number of questions is really not a serious problem. The complexity of questions is a problem, but not. So other ways of, apart of using these strategies, in order to reduce the number of questions, the idea is to have an oracle represent the user. You can use trusted specifications. We can talk about this a little bit later. Or use assertions. Many people have systems that include assertions saying, okay, this was wrong, it was okay. And maybe the debugger can use these assertions to determine if a node is valid or non-valid without asking. The idea of trusted specifications is that you have another program which you trust. Well, you can say, this is very easy to say, but this is not usually the case. In fact, sometimes it's the case, because in many cases you have a program that is working. You have tested and you trust the program. Maybe it's not, but in all the cases you have tried this work. And maybe you improve this program. Or maybe it was just a prototype and you make a different implementation in a different language. And the new implementation doesn't work. Then you can use the old program to debug the new one. Probably they are different. Probably, sure, the new program has new methods or new components. But some of them are the same. If some of them are the same and the semantics are the same, maybe you can use the trusted specification to debug the new program. This works, for instance, in SQL very well because usually you have a lot of views, SQL views connected, and maybe it's very slow. You try to improve and you get a new system, much better, but it doesn't work. And maybe you have some views which are common views, but you have changed the code. The name is the same, the semantics are the same, but you have changed the code. Then you can use the old version to debug the new one and save a lot of questions. Well, this is the end of this first part of the talk, and now we will go to the particular case of functional logic paradigm. I will go quite fast here because we just check a few examples to understand this. This functional logic paradigm is interesting from the point of view of declarative debugging because you mix all the features of logic and of functional programming. You have logic, variables, non-determinism, higher order, laziness, everything together. In the examples I will check here, I will use most of the functional features, but also a few logic features. For instance, here is a small program. Here is the natural number, 0, successor of number. The typical functional function take, that takes n elements of a list, takes 0 elements is the empty list, take any amount of elements from the empty list is the empty list, and take n plus 1 elements from this list is the same as take the first one and then take n from the rest of the list. Okay? We also have the function from, which returns a list of numbers starting in a number x. So it should return x, x plus 1, x plus 2, this infinite list. But it's wrong, because the first element is x, but the second element should be x plus 1. This is an error here, there is a lag. And we can throw this goal. I am using the functional logic language toy. Was developed here at the University Complutense. So we take two numbers from this list. Which is the expected answer? This should be x plus 1, x plus 2, and taking the first two numbers should be x and x plus 1. This is the expected answer. Taking two elements from this infinite list should be x, x plus 1. But we get this answer, x, x, and we know that this is a wrong answer. We expected here x plus 1. So we need to debug. And as I said before, we are interested in soundness. That's the reason we need a semantic calculus. Unfortunately, in our language in Toy, we have a semantic calculus. This is one. I will explain a little bit part of the calculus. No, it's not necessary to understand everything. Here we have this symbol bottom. Bottom means this is a computation that has whose result is not important, has not been computed or anything. It's very important for laziness. When some expression is not evaluated, then it's reduced to bottom. Then I don't care about this function call. So everything can be reduced to bottom because we are in a lazy language. We have also here, for instance, the decomposition. If we have two terms, h with some arguments, and again h with other arguments, reducing this to this means reducing each argument to the corresponding argument. It's easy. I will skip this one, and this is the function application, which is more complicated, but this I will please with the first part, which is important now. if I have an instance, a program instance rule of this form, f of tn is reduced to r. These are conditions that must be fulfilled. Then I have this function call. What we must do is to reduce each argument e to the corresponding argument in the program rule. When we have done this, we have already that f of tn must be reduced to s, some value s. And s must be a value such that when applied to the rest of the arguments, produces t. It's quite complicated. I know we are working with a higher order environment, so this can return a pattern that can be applied to the rest of the arguments. But the idea is to evaluate this and produce this result, you must first evaluate the arguments and then prove that the function applied to these arguments produces some value such that can be applied to the rest of the arguments producing t. I know it's not very straightforward, but then we can take this goal at the beginning and use this semantic calculus to obtain the answer. In particular, we can use this, but replacing r by this result and obtain this tree. I know it's a big tree, but it explains how everything has been obtained. So, for instance, here, in order to apply take, first reduce this to some other argument. In this case, this argument, which is 2, is reduced to 2, applying the composition many times. Okay. And then use take to produce this result. Take 2 from this list produces this. Observe that here is the bottom. The reason is that although from produces an infinite list, we are only taking the computation only considers the first 2 elements of the list, because we are using take 2. And then the rest of the list is bottom, meaning that we don't care about the result. It hasn't been used in the computation. This is the idea of the proof tree. What is important about this calculus and about this proof tree is this box here. The reason it's in a different color is because only these nodes are useful for debugging. What is the reason? And this is, I know this is a little bit more complicated, but there is an idea I want to translate. The idea is that, for instance, with this inference, you cannot have a buggy node here. This cannot be buggy. What's the reason? The composition always works. If this is true and this is true, all the premises are true, then the conclusion is true as well. Because our logic says that. Okay, you can say, okay, this is true for all the inferences. Then you cannot have buggy nodes. This is not true because this inference has an extra premise, this one. This is the only inference that uses a program rule. So if this is true and this is true and this is true and this is true, but this is false, it can be proved, it's easy to prove, then the program rule is wrong. So all the inferences using this, and this are not important because these nodes cannot be valid. And we can prove formally that this cannot be valid. Only this can be valid, this one. And in particular, this one. We are interested in this one. Why? Because it has the arguments reduced to their most reduced form. Why are we interested in reducing the arguments? Because in this way, the questions are easier. So maybe this is a function call, but the function call has been reduced before applying the rule to some simpler value. Then we will show to the user the result of evaluating this person, not this person itself, which can be very, very complex. And we can prove formally, we have proved formally that only using these nodes, we can, which are here the squares, we can have an abbreviated proof tree, which is useful for debugging. So we have this, we only take the squares, the square facts here, and we have a new tree, this one. In this tree, as you see, there are no nested function calls because they have been replaced by the result, except in the root. But we know that the root has produced an erroneous result. So we have this is unexpected. We have this, and we know that this is unexpected because from x produces x and then x plus 1, so this is wrong. And here the debugger asks is from x produces something starting by x. This is true? Yes, from x must produce something starting by x and then another thing. So this is valid, this is true. This must be understood as, it's true that the first element of from x is x? Yes, it's true. This is valid. So this is the debugging node. And this is the output of the debugger. The debugger will say, okay, this is wrong. From is wrong. And this instance can help you to find why. So the debugger will point out to from as the source of the error. The theory is a little bit complicated, but I think at the end, understanding this is not so easy. Do you have questions or maybe this is the more? Yes.
Can you come back to the slide before?
Sorry.
No. Slide. Yes. You evaluate the arguments of
Yes.
the function,
But only partially. But only partially. Only to the point where needed during the computation. So, for instance, from was evaluated to x bottom. We must be very, very careful because we don't want to evaluate more. Because we could convert a terminating computation in a non-terminating computation. So this must be, I skip a lot of details, but this is important. That's the reason from is reduced to x bottom. Of course, this is not very easy to implement, but we have a program transformation and it works. And since this is the most complicated part of the talk, I think maybe we can try a different example. I have here a different example, and maybe we can. I know this part is more boring, so we will use the debugger of toy, and we will try to debug this program. I don't know why there's a letter lost here. Well, but we imagine that this is PPP, perm sort, permute, insert, is sort. Okay, we have here a program, but we are working with black box, so we don't need to check the program. Only need to know that there are some functions and the intended meaning. The intended meaning is very easy, so we can use this for debugging. The only difficult part could be this one. This is, I don't know if I can make this. Well, now at least we can see this. This is the non-deterministic choice. This is a function which is called this way, and it returns either the first argument or the second argument. This is a non-deterministic function. This is French Haskell that is usually the choice. Right? Choice any of the two arguments. The other ones are very easy. Perm sort, try to sort this list using some permutation technique, tries different permutations. Permute performs a permutation. Inserts using order, so it must insert an element in a list in the position, and is sort checks if a list is sort. Only knowing that we can debug the program. We can try the program. I have here the system toy, and we can try, for instance, this goal here. Permutation sort of 3, 2, 1. The expected answer, of course, is 1, 2, 3. Then we try the system, and we get this unexpected answer. 3. 2 elements are lost. Then we say it asks for more solutions because we are in a non-deterministic environment. But instead of asking for more solutions, we can say D means debug. Debug this computation. There was something wrong. An initial symptom. Then the transformer program is produced, the computation is repeated, and now we have here the computation tree. Here is, we can expand all the nodes, and we will use some strategy. For instance, this divide and query. And then we have these questions here, and we can try to know if they are valid or not. So the first one, permute 2-1 produces 2-1. Is 2-1 a permutation of 2-1? Yes, it's the identity permutation. It doesn't. Permutation is just to reorder the list, keeping the same elements. So this is right. And the first symbol means right, the second wrong, and the third one is trusted. Trusted means this is right, and don't ask me more about this function because it's always right. I trust this function. I want to use this now. But this is okay. Second one, we must insert 3 here. This is correct? No, obviously, no. Should be, probably 3 should be after 2. It's not clear. We must check the intended semantics very carefully, but in this case, of course, it shouldn't lose elements. Again, insert 3 here is not, because 1 has been lost. This is not okay. And finally, this is the non-deterministic choice. The non-deterministic choice of this list and this list can return this. Yes, because it returns both. First one, then another one, and this is one of the possibilities. Return the second one. So this is correct. And finally, insert 3 in the empty list returns the list with 3. Yes, this is true. So we say this is true, and it says that insert is wrong. The function insert is wrong. In particular, the second rule of function insert has produced a wrong bugging code. So we can go back to insert and check that insert has some error. The error is here. This is okay. Insert x in the empty list is x, but insert x here is inserted using non-determinism. Okay, it inserts actually in all the positions. I forgot before. It inserts in all the positions. One possibility is insert x as the first one, and the other possibility is keep y as the first one and insert x in the rest. But here, x has been lost. Should be x and then insert. So there is an error here, and the debugger, without checking the code, only checking the semantics. Sorry?
What has been lost is the y.
Yes, the y. I said x, sorry, it's the y. Yeah. Should be a list with y in the head and this in the body. Okay, so this is the debugger. This is included with the system toy, and it only works for wrong answers, not for missing answers. Fernando was working with missing answers. Okay, let's continue. Okay. So the abbreviated proof trees, also in mod, Adrian has used a similar approach with abbreviated proof trees and debugger, both for missing and for wrong answers. So the abbreviated proof trees only include those nodes that can be potentially missing. It's independent of the execution order, so the computation tree abstracts away execution order, and include elements in the most evaluated forms. The implementation has been implemented using program transformation. So this is in Spanish. Okay. What we do, we don't transform actually the source code because this is very very slow. We use an intermediate representation. So TOI produces a temporary file with the intermediate representation. We transform this intermediate representation, which is faster. So we skip some parts, like for instance, when you are compiling the transformer program, you don't need to check the types because the original program was well typed. You know that because you have been using the program to produce the initial symptom, so you could compile the initial program. It was well typed, sure. And the program transformation transforms well-typed programs in well-typed programs. We have proved this theoretically. So we can skip the type checking phase during the time. Well, now we see a little bit about SQL views and finish with this and a little bit of the Datalog. So this is the idea we are working now. There are only some preliminary results. We'll check this. I will skip part of this, but the idea is if you have a lot of views, correlated views, this means that V depends, for instance, here. This is an SQL select statement on V1 and V2. maybe V2 depends on V3, and so on. Then you can also use declarative debugging. In this case, the computation tree is very easy because it's the syntactic dependency tree. It doesn't depend on the computation. When you use V, you always use V1 and V2. So you can obtain directly the computation tree, like here. And the trees are usually small because you say you have 2,000 views connected. Even the biggest system have maybe a few hundreds, most. Both missing and wrong are covered because in our you have an answer for an SQL and you say this is wrong. Maybe because there is a tuple lost. Maybe because there is one tuple that you didn't expect. But both are covered by the same framework. We don't have the problem of termination because in SQL everything terminates. So we are covering all the possible errors. We are not considering recursive queries. Recursive queries, which are a kind of special kind of SQL queries. But not we consider all SQL possibilities. Well, the problem is that the answers for a query, as you know, you are usually working with huge databases, and answer can consist of 2,000 rows. And it's very difficult to say to the user, okay, you just expect this, select everything from employees, and you get 2,000 records. Is this right? It's very difficult to know that. That's the reason we are working different ways of solving this. The first one was to have a test case generator. So you have a lot of views, use the test case generator and obtain a small instances of the tables that check the views in all the possible, or in most of the possible ways. This is something similar to do in Java. And this is, we have this test case generator already, and it has been implemented in this agreeable in this system, which is a Datalog system that Fernando is going to talk about after this talk, the next talk. So we also use trusted specification, and it works well. We have a first version, maybe it's slow or incomplete. We produce a new version and it does not work. And then we can provide the trusted specification to the debugger. The debugger tries to use the trusted specification to save questions. So we also have some graphic interface, and we have two implementations, but this is not so important. I have an example here, but I think I don't want to be out of time, so but I have I have another point, another item. I have now 1 hour and a quarter, I think. I have 1 hour and a half. 14. Okay. Maybe I will come later. Here's a sample. This is an example of a tree, of a SQL tree. Here are the views. Usually not always in SQL, the leaves are the tables, because you have views that use other views, and at the end you have the tables, the database instance. And in our debugger we have the possibility of saying, I trust the tables, because now a buggy node can be a table. What's the meaning of having a buggy node as a table? This table has an erroneous data. So maybe the reason is not that you made any error writing the view, but you made some error inserting the data on the tables. So maybe this is the case. But you can say, I trust the tables, and you will ask about the tables. So let's go to the last case. This is more related to the next talk, to Fernando talk. This is a strange case of Datalog and declarative debugging. And when we started applying declarative debugging to databases, we started with Datalog. Datalog is a deductive database, and the syntax is very similar to Prolog. In fact, it's a restriction to Prolog. It's easier than Prolog because you don't have functions, which makes that everything is terminating, because you don't have infinite structures. And you only have a stratified negation, and you have a computation rule that uses bottom-up semantics, which cannot be used usually in Prolog because you have infinite computations, but here everything is finite, and you can really compute fixed points in this system, and you really get all the answers possible for each question. So it's a kind of very restricted Prolog, and we thought that it was the same ideas we have employed, or everyone have employed in Prolog from the beginning, were useful also in Datalog, but they are not. The reason is this part. This part is different from Prolog, the evaluation mechanism is different. So we can consider this example. In this example, we have two clauses. P of x if q of x, and q of x if p of x. This is of course a dummy program, but it's useful for us. In Prolog, this doesn't make sense. You have this depends on this depends on this, and if you try to do ask for this goal, you get a non-terminating computation. But in Datalog, you can ask for p of x. What it does is to try to build the set of facts that satisfy this goal. It starts with the empty set of facts, try to use the rules of the program to produce new facts, and repeats until a fixed point is reached. In this case, the fixed point is already the empty answer. It starts with the empty set of facts and say, okay, may I use this rule? No, because I don't have any instance for Q. May I use this rule? No, because I don't have any instance for P. Then I am finished with this answer. This goal returns this answer in Datalog. Okay, but we can imagine that we have this interpretation. P of A and Q of A. Maybe we have forgotten to include P of A as a fact here in the program. Maybe. But this is the intended interpretation. Therefore, this is the missing answer. Also, Q of A is a missing answer. We have two missing answers here. And we say, okay, we want to debug. And we have learned in the case of logic programming that when you have a missing answer, you have an uncovered atom. This atom is uncovered. And therefore, you have an incomplete predicate. And the debugger will say, okay, this predicate is incomplete. You forgot something in this predicate. But in Datalog, this is not true. And this was, well, we found this when we were proving that the old technique was valid, and the proof didn't work, and the proof didn't work, until we noticed that this is a special case. In this case, this is not uncovered in the sense of logic programming. The reason is that there is a substitution that, when applied here, says, okay, P of A can be proved if you have Q of A. And Q of A can be proved if you have P of A. This is, you can say, okay, this means that the program could produce P of A. Could produce. There is a predicate that can produce P of A. But it cannot because Q of A is not here. Okay, and why Q of A is not here and you come here? And you find yourself in a cycle. This doesn't happen in Prolog because this is non-terminating. So nobody has studied this case in Prolog because you don't have an initial symptom. But this happens. So this is a kind of new error. There is no declarative debugger that can say P is erroneous, because either P or Q is erroneous, but you don't know which one. So we cannot blame either P or Q alone. We can blame P and Q and say P and Q form an incomplete set of relations. And that's what happens in Datalog. In Datalog you have not only incomplete predicates, but sometimes you have incomplete sets. You can say to the user, consider P and Q. Both together are not enough. There's something missed there, but you don't know what. Maybe P, maybe Q. And what about computation trees? Well, what we found is that then computation trees are not valid, and you need computation graphs, because you have really cycles in this case. And you have valid circuits. So everything is different, and a little bit surprising because it was at the beginning very similar, and you find something new. And it's the only case we know where something different from computation trees are needed. Computation graphs in this case. So we can check this example, and we can try to debug this example. This is an example for the Earth and the Moon and the Sun, and we have a few predicates. I will try to understand this, and we will try to debug the problem. So it says, first, the Sun is a star. The Earth orbits around the Sun. The Moon orbits around the Earth. And we can make a transitivity, orbits a transitive relation. X orbits Y if X orbits Z and Z orbits Y. This is right. If I say that the Moon orbits the Earth, then the Moon orbits the Sun also. Because here, this is the Moon, Earth, Sun. This works. So this is the transitivity closure of orbits. We know that this is not terminating usually in Prolog, but in Datalog it's terminating, and we can use that. We also say that X is a planet if X orbits Y, Y is a star, but this is not enough because the Moon orbits the Sun also by this definition. So we add a new here, a new predicate, and we say X orbits Y, Y is a star, and there is nothing in between. There is no intermediate body between X and Y. In the case of the Moon and the Sun, there is something intermediate, the Earth. We are using not, and this predicate intermediate, and intermediate is defined here. X and Y have something intermediate if X orbits Y and Y and Z orbits Y. This is wrong. This is wrong because this should be Z. But this is a little bit complicated, and it's easy to make an error. So this error actually happened when we were programming. We were looking for a good example, and first write a program and then introduce the bug. Well, I introduced the bug without noticing, and this was the bug. So we decided to keep this bug, a good one. This should be set, because then Z is the intermediate between X and Y. For instance, between Moon and the Sun, there is the Earth. Moon orbits Earth, Earth orbits the Sun. Okay, then we have a program with an error. We throw this goal, for instance, in the Datalog system this, and in Datalog you don't obtain, as in Prolog, several answers. You obtain all the answers in the list. So here we expect only one answer, which should be planet Earth. But we get, in practice, this is wrong answer. Emptiness. Wrong, or missing. In Datalog, you obtain a single list with all the answers. If the list is incomplete, you can say that there is something missing, but the list is wrong, because it's not the list you expected. So in this case, wrong and missing are confused. And our debugger is useful both for missing, for wrong, which are the same, and there are no non-terminating programs, as in user SQL. So the debugger is valid for all the cases, in this case of Datalog. So we have a missing answer, and we use the debugger included in the Datalog system. And here is the debugging session. In this, the first question says, well, the questions in Datalog are also a little bit tricky. Is orbit sun the empty? This is quite difficult to, maybe a little bit at the beginning. In Datalog, the empty answer means fail. There is no answer for this goal. So it's false that the sun orbits the sun. This is okay. Yes, this is okay. The sun doesn't orbit the sun. So it's valid. Here we have orbits the Earth something. Is true when Y is the sun. Yes. In our model, the Earth only orbits the sun, so this is valid as well. If I have this intermediate Earth and sun, there is something in between the Earth and the sun. In our model, there is nothing. So this should fail. This should return the empty set, but it returns the same, which means yes, there is something between the Earth and the sun. This is not valid. We didn't expect this. It should fail and return the empty. Orbits the sun something is returns the empty. Yes, this is valid. The sun doesn't orbit something in our model, our simple model. And what orbits around the sun? Around the sun orbits the Earth directly and the moon because it orbits around the Earth. So we have these two answers. This is valid. These are the questions that the debugger asks. And then the debugger says that intermediate is wrong. Error in intermediate with this instance, which can be useful to find error. So this is the error, and we have the error, and the user is happy, not very happy. And that's all. I will this conclusion. So declarative debugging is a general framework for debugging. It's based on the semantics of the components. It can be applied to many different paradigms. I explained a few ones. I didn't explain Java. So also we have a couple of debuggers for Java, mod, another. And well, our experience implemented declarative debuggers. Why declarative debuggers are not very famous? We don't understand why, but one of the reasons I think in the university, at least in our case, usually the tools are quite humble. They don't include a lot of fancy things like save the tree, undo. We don't care about these things because usually we are not interested at first. We are interested in implementing the theory and obtaining and working too. And we have found when trying to use our debugger that these things are very important. So we think if we work and we continue adding new features to the debuggers, we will reach a really useful debugger for any language in practice. So, for instance, in Java, I can imagine that in the future you could use a declarative debugger first, and then the trace debugger to go into the method, or at least the declarative debugger to skip a lot of methods and know that only this group can be wrong, and then concentrate using the trace debugger. And that's all. So, thank you.
You want to go back to
I don't know if
it is time.
I prefer to have questions or
Please ask questions. Same for the language, no?
or I go for example.
One remark about Datalog is a little bit like SQL. Sometimes it should be very difficult to know if the answer is valid because it can have a very large amount of fact. And my intuition is that maybe in some case you're just interesting to know if there is an inclusion or not in a first minute.
Yes, you're right. We are working in that direction. What we are doing now, what we're working on is when the user says, okay, this is valid and you have a lot of rows, maybe this is too much. And at the beginning, because the problem both in Datalog and SQL is that at the beginning usually you have a short answer. You are asking for people who earn more than 2,000 euros and you have only 3 people. But then this view uses another one, which is employees, which has a lot of. And then the problem is that when you start, you can say, okay, this is wrong. Why this is wrong? Maybe because this row shouldn't be here. You know that, because you know that the initial set is wrong. Using this information, saying this is included, but there is something less or something missing, so using wrong and missing information, is very useful because then you can filter the next view. Say, okay, you said that this guy shouldn't be here, so I will use slicing, kind of a slicing, to concentrate the next view on the results producing this guy. And then you only say, do you think that these 3 rows should be included in this table, or is this the question you are asking? Yeah, we are working in this direction. We think this is very important. For instance, sometimes you have very typical in SQL. You say select everything from this view, and you get 0 rows. Well, at that moment you know that there is something either in the from or either in the from that has 0 rows, or the where has discarded everything, the where part of the SQL. Then you can go to the from directly, looking for you find anything that is empty, and without asking the user, you can go deep the tree looking for errors. So there are many things that can be done to SQL and in Datalog. As you said, both are related, and in fact, our first debugger for SQL uses Datalog in the end, because we use SQL, which is translated to Datalog. In the Datalog system, both are combined.
Is there any scaling problem applying the declarative debugging to Java to programs using library code? Or?
Yeah, the scaling problem about the size of the tree is the main problem. So the implementations, I think you said Silva and David are working with an implementation that use databases to store the tree. So the tree is stored on the fly on a database, and you can start debugging when the tree is incomplete, because you have already some parts. You don't need to produce the whole tree, and you can produce lazily parts of the tree.
The size of the tree depends on the length of the trace in
Yes.
the syntax.
Yes.
Not in the number of modules. Depends on the
Not directly, no, because you can have a lot of modules, and in a particular computation only use a few ones. Depends on the length of the trace. Yes. And also, I think in the debugger in HAT, which is a debugger for Haskell by Nielsen, they also produce the tree lazy.
How do you manage declarative debuggers manage higher order functions in general?
Higher order functions. Well, actually they are not a problem, because you are using a particular computation, and in this particular computation, higher order variables take an actual value, particular value, and this is represented in the tree.
Yeah, but if a function returns another function, and this is given to the oracle, how do you know if that is correct or not?
Well, you must know if you expect that a function returns another function. So it will say.
The oracle knows everything. The different question is how does it know it?
Yeah, but how do you show the function to the user, for example?
Oh, yeah.
It's a term.
Yeah, you mean that in Haskell it's not possible. This is because the representation, I think in the Glasgow Haskell machine, is not so easy to get the name for the function with the. But this is a problem of representation, I think. In our system, we have the representation as it is. So you have f of 1, and this is a partial application. You have f of 1 as term, and you can display this as term. So we don't have that problem. But I have read by some people that in Haskell they have some problems obtaining the representation of partial applications. Of course, we don't have lambda, because if you have a lambda, also you have a problem to represent this.
Like the source code of that function instead of
The idea is that the one answering the questions, the first thing is understanding the question, and this is the part of the decision in designing the debugger. Which kind of things are you going? So in the case of what Daniel did in his thesis for mod, we also have some things that we decided not to ask the user about that, because it includes things that in principle are not even taught typically when you are explaining things about reducing terms. So this is not the kind of thing you're going to put in questions. So that's a design decision. And then once you put things there, the first thing is how you represent. So one of the latest papers we wrote together with Rafael precisely is what to do with things that are lazy, how to represent them, what do you put in that information, okay, and how do you abbreviate it for the user. Any other question? So thank you very much, Rafa.